owe it to him because he was there when we needed the guidance and the support. And with immense pleasure, I would like to introduce our today's resource speaker, Dr. Manmohan Lal Satnami sir. I welcome you, sir, in today's session. And without any further delay, I would like to introduce him to you all. Dr. Manmohan Lal Satnami is currently working as the Senior Assistant Professor in School of Studies in Chemistry, Pandit Ravi Shankar Shukla University, Raipur. Sir has completed his PG from the UTD, PTRSU, the same institution where he completed his PG. After that, he earned his MPhil from Vikram University, Ujjain, followed by his PhD from Ravi Shankar Shukla University, Raipur. During his illustrious scientific career, he held position as a postdoctoral researcher from the Federal University of Santa Catarina, Brazil. Sir has visited many foreign countries like Brazil, Argentina, Malaysia during his quest for scientific explorations, leaving a profound impact on the numerous students like me. Sir is having a teaching experience of 15 years in which he has nurtured and helped his students grow. His research experience also encompasses a time span of 15 years in the fields of nanomaterials, physical and organic chemistry, and surface science. A proof of which are the research papers being published in various journals of high impact factor. More than 80 research papers have been published on his name, out of which 8 papers have been published in American Chemical Society journals, 6 papers have been published in Royal Chemical Society journals, 28 papers in Elsevier journals, and the rest of the papers in Wiley, Springer, and other renowned journals. Working as a research supervisor, 5 scholars have been awarded their PhD under him. One is having his thesis submitted and 2 are currently working under him. 10 students have been awarded their MPhil under his supervision. 3 research projects have been completed in his guidance: the DST Fast Track project, the CCOS project, and a project from SERB EEQ. In his dynamic career, Sir has achieved his lap of honor by various awards that were given to him. The first was the TWAS CNPQ Award, that means the World of Academy of Science, National Council for Scientific and Technological Development Award. He was awarded that as a postdoctoral award in Brazil. The DST Fast Track Award. Another feather in his cap is the UGC Research Award, the Young Scientist Award, and of course, the year in which I passed out from the university, he has been awarded the University Best Teacher Award. Being the scientific enthusiast, he was the part of organizing committee. As the organizing secretary, he became the part of 22nd CSIR National Symposium in Chemistry 2018, 56th Annual Convention of Chemists 2019, and an International Conference on Recent Trends in Chemical Sciences 2019. So with a sea of respect and love for the professor, mentor, and a wonderful human being that he is, I once again welcome Dr. Manmohan Lal Satnami among us for his talk on nanomaterials-based Fred donor acceptor pairs for sensing applications. You are very, very welcome, sir. And now I hand over the session to you.
Thank you, Vandana. Thank you very much for your nice introduction. और तुमने वो सब बोल डाला जो मैंने लिख के दिया.
Yes.
इतना कुछ बोलने की जरूरत नहीं थी.
Sir, please.
Actually, I'm excited. I'm very happy to say that you people are joined here, and so many people I can recognize. And before starting my lecture, I would like to thank organizers for giving me this opportunity to talk to people like you, the people of the chemistry fraternity. And I really very like to convey my message, my talk to the young people like you. And most of thing I will talk about is my research work, but I will try to say some basics. और कोशिश करूंगा कि बीच में कभी कुछ स्टोरी सुनाऊं, याद आ जाए तो. And please ignore if there is any kind of discrepancy during my presentation. And this platform is not very good, as I told you earlier, for interaction, because I cannot see you people while presenting. So if there is no eye contact, the conversation cannot be made in dialogue mode. It's simply a monologue mode. So better if opportunity comes in future, we will meet together, we will assemble, and we will try to organize any conference so that you all young people can assemble in the same building and we can have very good discussion. So with this, let I try to share my slides and you people please tell me if it is visible. Okay.
Yes, sir.
Okay. My slide is visible to you.
Yes, sir.
Okay. Am I audible?
Yes, sir.
Okay. Very good. So now I'm putting in slideshow mode. That's okay.
Yes, sir. It is
Okay.
fine.
So dear friends, today I will talk about the nanomaterial based phase donor acceptor pairs for sensing application. So now question arises, what is freight? The first question should be what is freight? So freight is fluorescence resonance energy transfer. Sometimes it is called Foster resonance energy transfer. So now what is uh, Foster resonance energy transfer or fluorescence resonance energy transfer? Say, if there is a molecule and the molecule is excited with a certain amount of energy and the molecule is fluorophore, fluorophore means a fluorescent molecule, then molecule will be excited and when it will come back to the ground state, it will release energy in the form of light. And say there is another molecule or any ion, yeah, nanomaterial system that is present with the fluorescent molecule, then what could happen? The amount of energy that is being released in the form of light by the fluorescent molecule can be accepted by any acceptor molecule or something nanomaterial. Then what is phenomena now? The fluorescence energy of fluorescent molecule is being transferred to the any acceptor molecule. So this phenomena is called freight. And during this freight process, what will happen if the energy is transferred from fluorescent molecule to the any acceptor molecule, then the fluorescence of fluorescent molecule or any nanomaterial or any quantum dot will decrease. So using this phenomena, we have, with the help of my student, developed many sensors for detection of different kind of analytes. So this is the basic of the story. So before going to the story, okay, let I show you the content, what I am going to talk about. I will talk about quantum dots, carbon quantum dots, that is Fred donor, both are the Fred donor actually. And what are the Fred acceptors? Like I will talk about the gold nanoparticle, gold nanorods, magnesium oxide nanowires. Even though the magnesium oxide nano rods, nano seeds are also very good threat acceptor, but since I have worked with the nanowire, then I will talk about MnO2 nanowires. Then I will talk about the freight-based sensor for detection of acetylcholine esterase, which is an enzyme, pesticides, cholesterol, hydrogen peroxide, and glutathione. So these I will talk about. So before going to the detail, since we all are teachers and we are teaching to the graduate and postgraduate students, so with my practice, you can say, or experience, I would like to say something in this slide. See, this is the very basic spectroscopic technique. It is my experience when I go to class and I ask my students, what are the different spectroscopic technique you know, and even you can do with your students, and you will get surprising answers. If you ask question, what are the different spectroscopic technique you know, certainly you will find student will name other than UV visual spectroscopic technique. They will say NMR, they will say ESR, they will say about the mass spectrometry, IR, other techniques. And they actually don't name UV visible spectroscopic technique because they feel that this is basic, very, very simple. So if I name UV visible spectroscopic technique, people will laugh on me. This is actually the thinking of students. But most of the students, even the postgraduate students, don't understand this spectroscopic technique and its importance. So but we are teacher, we understand, but I would like to share something to you. Okay, so this is very basic. You can see the top left side of the figure. It shows a UV visible spectra. It's a schematic representation. Okay, so this spectra can be divided into 4 sections. See, if this spectra is shifted towards left, this is called blue shift. And if the spectra is shifted towards right, means higher wavelength, then this is called red shift. If the absorbance of this spectra is increases, then this is called hyperchromic shift. And if the absorbance of this spectra is decreases, this is called hypochromic shift. And all the 4 types of spectral shift in UV visible spectra are very, very important. And on the ground of these, we have designed our research work. See, right hand side. Could you see? Hello?
Yes, sir. It
Yes.
is visible, sir.
So my cursor is visible to you?
Sir.
So top right side, you see, this is the UV visible spectra of gold nanoparticle. See, gold nanoparticle gives UV visible spectra maximum at 520 nanometers C. Okay, then you can see another spectra around 650 700, है ना? तो यहाँ पे भी एक स्पेक्ट्रा आपको उठता हुआ दिख रहा है. So what is actually happening? Gold nanoparticle gives absorption at 520 nanometer. If the size of gold nanoparticle increases, its wavelength will be shifted towards higher wavelength. So see, there is only gold nanoparticle at the top. See here. So it will give only one spectra. Oh, sorry. Okay, then let me add sodium chloride to the gold nanoparticle, then aggregation will start and it will give spectra at around maximum at 650 or 655, you can say. Okay, so what is happening? Happening is that the concentration of gold nanoparticle is decreasing. Therefore, the absorbance at 520 nanometer is decreasing. And at the same time, as it is decreasing, the absorbance at 655 nanometer is increasing. What it indicates? It indicates that if the spectral shift happens towards right, it means the species which was existed previously is now converted to another species. Okay, so what information we get from here? We get that if any species will convert into another species, there will be red shift or blue shift. Okay, see, and if the concentration of any species, any molecule is decreasing, then the absorbance of the spectra will be hypochromic shift, will decrease. Understand? And see, if we put a very little amount of any compound and we took the absorbance of that molecule, that it will give you absorbance at maybe at 0.1. And if we increase the concentration, then absorbance will increase. See, there will be what? hyperchromic shift. And in between these two peaks, see, at 520 and 655, when the absorbance at 520 is decreasing and 655 is increasing, in between these two graphs, you can say maximum, there is a point which is not clear here for gold nanoparticle, but if you see here, this is for paranitrophenol. See, फिगर नंबर सी लिखा हुआ है जहां पे, वहां पे देखिए, you see this is absorbance for any paranitrophenol like molecule, and this is the point at which this species is converted to this species. Okay, so it is giving absorbance at 400 nanometer. This is for what? This is for paranitrophenol. तो आप अपने बच्चों को, अपने स्टूडेंट को ये एक एक्सपेरिमेंट असाइन कर सकते हैं. आपके लिए में पैरानाइट्रोफिनॉल होगा. You take paranitrophenol in a beaker, dissolve it in water, and put some amount of sodium hydroxide and measure the absorbance. And जैसे जैसे आप सोडियम हाइड्रोक्साइड का अमाउंट बढ़ाते जाएंगे, तो the concentration of paranitrophenol will decrease and paranitrophenol ion will increase, because the pK of paranitrophenol is 7.2. So if you provide the pH more than 7.2, say for example 7.5, then paranitrophenol ion will form. So this is the fundamental, and using these fundamentals, we have designed our research work. So that I will show you in next slide. This process everybody knows. This is Jablonski diagram. Okay.
Yes, sir.
So please, sometimes I will ask you, you answer me. Okay.
Yes, sir. Yes, sir.
Okay. So this is Jablonski diagram. Everybody knows. If any molecule is excited with certain amount of energy, the molecule will go to the excited state. It could go to the first excited state, and it can go to the higher excited state. Then what will be the fate of the molecule when it is excited? उस molecule का भविष्य क्या होगा कि when it is excited? So what can happen? So see, if any molecule is excited, it goes to the excited state, then there could be any change in the molecule. ठीक है, उस मॉलिक्यूल में कुछ चेंज हो सकता है. से फॉर एग्जांपल देयर इज अ मॉलिक्यूल लाइक कोई एरोमेटिक मॉलिक्यूल है, कोई कंपाउंड है, आपने एक्साइट कर दिया, ठीक है, तो देयर विल बी रेडिकल फॉर्मेशन. तो अगर रेडिकल फॉर्मेशन हो गया तो रेडिकल इज अनस्टेबल. द सेम मॉलिक्यूल विल हैव अनदर रेडिकल, तो बोथ द रेडिकल कैन कंबाइन टू फॉर्म अ मॉलिक्यूल, न्यू मॉलिक्यूल. दैट इज व्हाट डाइमेराइजेशन. ठीक है, तो वो उस मॉलिक्यूल में कोई केमिकल चेंजेस हो सकता है, केमिकल रिएक्शन हो सकता है, ये एक बात हो सकता है. या फिर ये दिस अमाउंट ऑफ एनर्जी कुड बी ट्रांसफर्ड टू एनी मॉलिक्यूल which is not being excited directly by giving energy. So this is what photosensitization process. What can further happen? Say if the molecule is excited to the S2 state, then through the internal conversion, the molecule can come back to the S1 state, and from S1 state, this energy can be released in the form of fluorescence. When the molecule will come back to the ground state, this can happen. And further, what can happen if the first excited state में कोई इंटर सिस्टम क्रॉसिंग हो, ठीक है ना, द पेरिटी ऑफ द मॉलिक्यूल, यू कैन से व्हाट इज इट इज कॉल्ड सिंगलेट. यस, दिस इज सिंगलेट स्टेट. ओके, व्हेन इट इज कन्वर्टेड इनटू ट्रिपलेट स्टेट, ठीक है, तो द सिस्टम इज कॉल्ड इंटर सिस्टम क्रॉसिंग. Then this molecule can, through inter-system crossing, it can come to the triplet state. And when it releases its energy in the form of radiation, then the process is called what? Phosphorescence. Okay, let's come back. Again, the molecule is excited to higher excited state. Through internal conversion, it came to the singlet state, first excited state, and it is releasing the energy in the form of fluorescence. And before it releases the energy in the form of fluorescence, any other species, foreign species, comes in contact with the molecule, then what will happen? The amount of energy which is being emitted in the form of fluorescence can be absorbed by the acceptor. So this is what? This is freight. So because of the freight process, the fluorescence जो होने वाला था, that will be stopped. So this process is called what? Quenching, fluorescence quenching. Okay. Okay. So for
Yes,
the
sir.
freight process, any kind of freight process, two things are very important. Number one, the species which gives fluorescence. So now from here I will say the nanomaterial. Okay. So because we are talking about the nanomaterial, then I will say nanomaterial. तो किसी भी सिस्टम में, किसी भी नैनो मटेरियल सिस्टम में, फ्रेट सिस्टम होने के लिए two things are important, two things are required. Number one, the nanomaterial which gives fluorescence. Okay, and another nanomaterial which can accept the energy which is being released from any fluorescent molecule in the form of fluorescence. Okay, so quantum dot are very good candidates which gives fluorescence, and quantum dots are much better than a fluorescent dye. The question may arise that if there is so many fluorescence dyes are available, then why quantum dots can be used in the place of your fluorescent dye? So answer is a very simple, that all the fluorescent dyes are organic molecules and there are conjugated bonds. So when it is excited with a high energy in the range of UV, then the molecule could go to the photo degradation. But this is not happens with the quantum dots. Okay, so what is quantum dot? So quantum dots can be characterized into two general categories. Number one, the semiconductor nanocrystal materials like CDT, ZNS, CDS, CDAC, these all are quantum dots. And another kind of quantum dot could be originated from carbonaceous species, which are basically what? Organic species. So that kind of quantum dots are called carbon quantum dots. If the carbon quantum dots are derived from the graphene, yeah, graphene oxide, then it is called graphene quantum dots. Okay. So see, you can see from this picture from the left hand side, if you can see my cursor, the semiconductor quantum dots like CDT, yeah, CDSE gives size dependent fluorescence. You can see, you see all these tubes. The tubes are illuminated under the UV light, and it gives different color from bluish to reddish. The material is same. These all are what? These materials are actually synthesized in my laboratory. तो दिस ऑल आर CDTE, सभी का जो केमिकल कंपोजिशन है वो दैट इज CDTE ही है, लेकिन साइज आर डिफरेंट. तो अगर इनका साइज अलग अलग होगा तो इट emits different color. So if size is smaller, say for example, if the size is 1.5 nanometer, then it will emit blue color. If the size is around 6 nanometer, it will emit red color. So quantum dots are nanomaterial which size are less than 10 nanometer. तो क्वांटम डॉट का जो साइज होता है वो 10 नैनोमीटर से कम होता है, देन इवन क्वांटम कंफाइनमेंट कैन हैपन. ठीक है, और 10 नैनोमीटर से ऊपर का साइज का कोई मटेरियल है तो दैट कैन बी कैरेक्टराइज्ड एज नैनो पार्टिकल्स. एक्सक्यूज मी, जस्ट सेकंड, आई एम रिसीविंग वन कॉल. हेलो, नमस्कार सर. सर मैं भी लेक्चर में थोड़ा देर बाद लगाता हूँ आपको 1.5 घंटे में. जी जी जी, ओके. सो ये दिस गिव्स साइज डिपेंडेंट इमिशन. तो अभी आपने सुना होगा कि सैमसंग ने एक नया एलईडी टीवी मार्केट में लाया है, and it is called quantum dot
True.
LED. So that quantum dot LED is actually the display is, the screen is, the panel is completely based on this technology, this technique. Okay, see, from here you can see the different fluorescence spectra of all these quantum dots. At the right hand side you can see carbon quantum dot that will be prepared in our laboratory. You see we have prepared blue emission, green emission, orange emission, and red emission carbon quantum dots. So these all are the fluorescence spectra of all the carbon quantum dots. Okay, so let I move to next slide. Okay, yes. So uh, we can compare the properties of semiconductor quantum dot and carbon quantum dot. This FWHM. Oh, hello. सर मैं लेक्चर में समय थोड़ी देर लगाऊं? ओके, जस्ट सेकंड, ओके प्लीज. यस, सो यहाँ पे मैंने एक स्पेक्ट्रम में आपको दिखाया हुआ है FWHM. Do you know what is this FWHM? This is called full width half maximum. Full width half maximum means the width कहाँ पे, ये दिस इज फुल हाइट ऑफ द स्पेक्ट्रा और इसका हाफ ये है, तो इसके बीच का जो 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 डिस्टेंस है यू कैन से, ठीक है, इट इज कॉल्ड फुल विड्थ हाफ मैक्सिमम. फुल विड्थ हाफ मैक्सिमम. सो if there is any organic molecule it absorbs energy and it gives you absorption spectra. तो absorption spectra बहुत broad हो सकता है और बहुत शार्प भी हो सकता है, ठीक है. तो for any quantum dot या any emitting nanomaterial, their full width half maximum should be minimum, and if it is around 90 nanometer then it is very good. So both the semiconductor quantum dot and carbon quantum dot gives the full width half maximum at around 90 nanometer. So these are the band gap of quantum dots. तो एक्चुअली बैंड गैप के बेसिस पे ये इमिशन देता है. ओके, सो हियर in the carbon quantum dots, the energy state arises between pi and pi antibonding. Later I will discuss. Okay, transition, and in between, if there is nitrogen doping in carbon quantum dot, then another energy states will arise. So what I am trying to tell you that the fluorescence of carbon quantum dot is because of all these energy transitions. See, all the energy transitions, and the fluorescent emission of the semiconductor quantum dots are because of this energy transition, conduction band, valence band to conduction band transition. Here you can see the fluorescence lifetime decay curve of semiconducting carbon quantum dot. So this shows that the fluorescence lifetime of semiconducting quantum dots are generally in between 20 to 50 nanosecond. But in the case of carbon quantum dot, the fluorescence lifetimes are below the 10 nanosecond. So these are the different parameters. On the basis of this parameter, we can compare the quantum dots, normal quantum dot, conventional quantum dot, and carbon quantum dots. These are the different applications of quantum dots, comprises of semiconductor quantum dots and carbon quantum dots. Okay, so any of the nanomaterial, if it is bare nanomaterial, then it can have limited application. Say for example, if there is any semiconducting quantum dots, then that semiconductor quantum dots can be used for the solar applications. But if it has to be used in biological system, then it cannot be used. It cannot be used because it cannot now interact with the biological molecules. So to interact with the biological molecules, the surface of quantum dots should be functionalized with different functional group. So these are the different functional group through which the surface of quantum dots can be functionalized, and through this functional group any of the biological molecule can form a bond. Interaction could be different if the surface of this quantum dot is negatively charged and any biological molecule is positively charged, then there could be the electrostatic interaction. But if any biological molecule contains carboxylic group and we have functionalized this surface with amine group, then there could be amide bond formation between biological molecule and this quantum dot, so that the biological molecule can bind with the surface of quantum dots, and whatever the application you want to perform, you can do it. Okay, so this is our research work. So you can remember that when I was talking about when I begin my lecture, I was talking about the UV visible spectra. See, and I told you that utilizing this phenomena, we developed one sensor, and what we did actually, see, we prepared gold nanoparticle which was capped with citrate. तो citrate capped gold nanoparticle भी prepared. फिर हमने क्या किया, हमने इस गोल्ड नैनो पार्टिकल में एक एंजाइम मिलाया एसिटिल कोलाइन एस्टरेज, और इसी में मिलाया एसिटिल थायोकोलिन. ओके, सो व्हाट वी डिड एक्चुअली, we took gold nanoparticle, we added acetylcholine esterase. It is one enzyme that actually regulate our nervous system, and acetylcholine is actually the, how to say, acetylcholine esterase. Acetylcholine is actually neurotransmitter. So instead of taking acetylcholine, we took acetylcholine. Okay, so I repeat. We took gold nanoparticle, we added acetylcholine, and further we added acetylcholine esterase. Then what happened? The color of this gold nanoparticle, which was red, became blue. So what happened actually? So happened is what? In the presence of acetylcholine esterase, the acetylcholine is hydrolyzed to form acetic acid and a thiol containing group. Okay, so this sulfur of thiol containing group is very good. It shows very good affinity with gold nanoparticle because of soft acid base principle. So this sulfur, when bind with the surface of gold nanoparticle, it induced aggregation. And as the gold nanoparticle is aggregated, its size increases, and if its size will increase, the color will change reddish to blue, and it will give absorption at 655 nanometer. You can see from here, and this is the absorption at 520 nanometer is for gold nanoparticle. As the size of gold nanoparticle is increasing, the amount of absorbance at 655 nanometer is increasing, and at 520 nanometer is decreasing. Okay, then what we did? We did same thing. We added acetylcholine, acetylcholine esterase, and we added organophosphorus pesticide. So organophosphorus pesticide actually inhibits the activity of acetylcholine esterase enzyme. So the activity of acetylcholine esterase enzyme is inhibited. Now it will not catalyze the hydrolysis of acetylcholine, and if it will not hydrolyze, then the sulfur group will not bind with the gold nanoparticle, aggregation will not happen, and the color will be remain red. See the red color, and it will give absorbance at 520 nanometer. Then further what we did, since the enzyme acetylcholine esterase is inhibited, we added some reactivators. और आपको शायद पता होगा मार्केट में एक पिरिलिडॉक्सिन करके एक रिएक्टिवेटर अवेलेबल है. जब किसी व्यक्ति को ऑर्गेनोफॉस्फोरस कंपाउंड से एक्सपोज हो जाए, जैसे सेरिन गैस आपने सुना होगा, जो सीरिया में सेरिन गैस का अटैक हुआ था, दैट इज आल्सो ऑर्गेनोफॉस्फोरस कंपाउंड. एंड that is very, very bad, you can say, inhibitor of acetylcholinesterase. So the same phenomena happens. Okay, so we added reactivator. This reactivator reactivates acetylcholinesterase activity. Hello? हेलो, कहीं से मुझे आवाज सुनाई दे रहा है? आर यू ऑन द लाइन?
It was interruption.
तो थोड़ा माइक बंद करवा दीजिए.
Please kindly, I request all the participants to please switch off their mic and mute it. Thank you.
Okay, so when we added oxime like reactivator, the enzyme become activated, and again the first phenomena happens, and aggregation of gold nanoparticle again started, and it gave once again the absorption at 655 nanometer. So on the basis of these ground, we determine the amount of pesticide. Okay, so these are the optimization, you can say, what we perform during the paper, writing paper. Yes. In another work, we publish is a carbon quantum dot gold nanoparticle system as a proof for the inhibition and reactivation of acetylcholinesterase detection of pesticides. So this was the title of paper. So this paper is actually based on, this work is actually based on the Fred process. So the carbon quantum dot here is a Fred donor, and gold nanoparticle is a Fred acceptor. So what we did actually, see what happens actually. Okay, see, we prepare carbon quantum dot through hydrothermal route, and इस कार्बन क्वांटम डॉट में हमने गोल्ड नैनो पार्टिकल मिलाया. द फ्लोरेसेंस इंटेंसिटी ऑफ कार्बन क्वांटम डॉट इज डिक्रीज. क्यों हो गया ऐसा? बिकॉज द एनर्जी of carbon quantum dot is transferred to the gold nanoparticle. Then fluorescence quenching is happening with this carbon quantum dot. Then after adding gold nanoparticle, we added acetylcholinesterase enzyme and acetylthiocholine. तो ये acetylcholinesterase enzyme catalyze the hydrolysis of acetylthiocholine, and thiocholine is produced, which is sulfur containing compound. Okay, then as this thiol containing compound is released, this thiol containing compound will interact with this gold nanoparticle. The gold nanoparticle will start aggregation, and its size will increase, and as the size of this gold nanoparticle will increase, it will release from the surface of quantum dot, carbon quantum dot, and therefore the fluorescence intensity of this carbon quantum dot will recover. So this is called fluorescence recovery. The process is called turn on. The fluorescence turn on. So you can see this is now looking fluorescent. Okay, दूसरी तरफ हमने क्या किया? We took carbon quantum dot, we added gold nanoparticle, fluorescence quenching happened, then acetylcholinesterase वैसे ही मिलाया, then we added acetylthiocholine, then after this we added organophosphorus pesticide. So organophosphorus pesticide will inhibit the activity of acetylcholinesterase. Then the process what was happening in upper end of this figure will not happen. So तो क्या होगा? तो then the fluorescence quenching will be continue. Then further we added reactivator, oxime's reactivator. The inhibited acetylcholinesterase enzyme is reactivated and it start functioning. Then what will happen once again? The acetylthiocholine will hydrolyze, it will give you thiocholine, and thiocholine will interact with gold nanoparticle. Gold nanoparticle will start aggregation, and fluorescence will recover. So this is the hypothesis that we designed to construct fluorescence Fred-based sensor for the detection of pesticides. So you can see from here, when the gold nanoparticle is interacting with carbon quantum dot, the fluorescence intensity is decreasing continuously. See here. Okay, and from the right hand side, top right hand side, you can see the fluorescence spectra that the fluorescence intensity is increasing. So this is increasing because of what? Aggregation of gold nanoparticle. When it was only normal process, and when it was inhibited by pesticide, then reactivated by any reactivators. So on the ground of this, we designed the sensor for the detection of pesticides. So are you on the line?
Yes,
Hello?
yes,
Yes,
sir.
sir.
ओके सो मैं बोलता ही रहूंगा तो ऐसा ना हो कि कोई सुन नहीं रहा है. ओके
Sure, sir. We are listening, sir.
ओके ओके थैंक यू थैंक यू थैंक यू. Okay, so how did we prepare carbon quantum dot? So we prepared carbon quantum dot by the pyrolysis of citric acid, and gold nanoparticle was prepared by citrate capping that you know well, I think. Okay, so how a citric acid gives carbon quantum dot? See, so the citric acid, see 1 2 3 4, there are 4 5 molecules of citric acid. ठीक है, तो जब पैरोलिसिस होता है तो व्हाट विल हैपन, देयर विल बी डिहाइड्रेशन. सी दिस O and this OH will form a water, and after this the dehydration, a carbonization process happens and carbon quantum dot is formed. But if we try to, we are trying to prepare a nitrogen doped carbon quantum dot, then this is citric acid and urea. If both these molecules are treated in a hydrothermal autoclave, the same type of phenomena, the dehydration, then carbonization process happen to give carbon quantum dot. And if you want to read further, you can refer these two papers, Carbon 2012 and RSC Advanced 2015. Okay, so you can see from here that what carbon quantum dot we prepared. It looks bluish in under the UV light, and it gives absorption spectra maximum at 355, and emission at around, I think it is um, 5 500 nanometer. I think it's looking 470, not 500. See, and this carbon quantum dot gives fluorescence excitation dependent emission. You can see, है ना, जैसे जैसे excitation wavelength we are increasing, the fluorescence spectra is shifting and intensity is decreasing. This is FTIR spectra of carbon quantum dot. Through this, we actually characterize the surface of carbon quantum dots. Means what are the different functional groups are present in the surface of carbon quantum dot. So you can see from this figure that the carbonyl group, COH carboxylic group, somewhere hydroxyl group are present. Here it's a zeta potential measurement we perform for the carbon quantum dot and gold nanoparticle. So you can see the zeta potential value for carbon quantum dot is positive, and zeta potential of gold nanoparticle is negative, and therefore the negative positive can have a very good electrostatic interaction between gold nanoparticle and carbon quantum dot, so that both the molecule can come closer to have the effective Freight process between them. Of course, this is gold nanoparticle we characterize through TEM image. Yes, the most important thing for thread process to happen is there should be the overlap between the fluorescence spectra of carbon quantum dot and absorption spectra of gold nanoparticle. So you can see from figure B, if you can see from there, the blue line is the emission spectra of carbon quantum dot, and the black line is absorption spectra of gold nanoparticle, and both are overlapping. So this is very important. And another point that is very important is that if any quencher or any fluorescence receptor is present with a fluorescent donor, say for example carbon quantum dot, then the fluorescence lifetime of carbon quantum dot should be decreased. So see, you can see this is the red line is fluorescent decay curve for carbon quantum dot, which is excited at 468 nanometer, emission at 468 nanometer. And when gold nanoparticle is added to the carbon quantum dot, है ना, then the blue green line appears. Okay, curve for the donor and acceptor pair.
एक मिनट में लेफ्ट हो तो मैं ज्वाइन करूँ करके देखता हूँ।
अरे तो भाई लेफ्ट
It
नहीं कर
means,
रहे हो। अच्छा उधर
hello,
से लेफ्ट हुआ तो ज्वाइन करोगे।
hello.
Sorry, sir, it was another interruption. As we have requested, all of you, please you mute your mic because it is very, unprofessional to
नहीं मैम ज्वाइन नहीं हुआ।
put on your mic.
I'm continuing. Okay. But I mean to say that the fluorescence lifetime of carbon quantum dot will decrease in the presence of a gold nanoparticle, and on the basis of the fluorescence lifetime of donor and donor acceptor pair, we can calculate the fret efficiency, mean the amount of fret happening between carbon quantum dot and gold nanoparticle. And these slides shows the linear regression for determination of pesticide and gold nanoparticles. Okay. So, see, this is the work which we have recently published in ACS Applied Nanomaterial. One of my good student, Miss Lakshita Devangan, she performed all the experiments, and now she has actually submitted her thesis. Soon she will be doctor, and I'm very much glad with her performance. During this pandemic period, there was lockdown for the 1.5 year, and with these all constraints, she did this very good work. So what we did actually, we prepared nitrogen doped carbon quantum dot and manganese oxide nanowire, and we use these nitrogen doped carbon quantum dot and MnO2 nanowires as a freight pair for detection of cholesterol, glutathione. You know it. This is very good antioxidant. Acetylcholine esterase enzyme we determined, and we detected the chlorpyrifos, which is organophosphorus pesticides. Okay, so how did we hypothesized? Actually, we all the teachers and most of us, maybe we are engaged in research work. और शायद जब शायद घोष साहब का जब लेक्चर हुआ होगा तो आपने सुना होगा, वो कहते हैं, उनका कहना है, इस माय टीचर, कि रिसर्च वेयर यू आर, रिसर्च वेयर यू आर। तो आप जहां पर भी हैं वहां पर रिसर्च कीजिए विथ योर एक्सिस्टिंग फैसिलिटीज. So we cannot blame with the things that we do not have facilities, we do not have this that, so we cannot do the work. No, ऐसा नहीं है. हम अपने एक्सिस्टिंग फैसिलिटी में काम कर सकते हैं, ठीक है, लेकिन काम करने के लिए सबसे इंपॉर्टेंट चीज है वो ये है कि आप अपने रिसर्च वर्क को अपने टेबल में कैसे डिजाइन करते हैं. तो एवरी गुड रिसर्च वर्क could be, should be, would be design and must be designed in the table, on the table, and then on the basis of that hypothesis you can perform your experiments, and on the basis of your experimental findings you can interpret your results, and you can have a very good research, not paper. Paper is the final thing. Okay, so if we have done good amount of work, we have done something good, then we can publish paper. But the importance is to have a good research work. Paper comes later. Okay, so what we hypothesize actually, that is shown schematically in this figure. See, we prepared carbon quantum dot using citric acid and triethylamine as a precursor. So triethylamine we use as a nitrogen source, and citric acid as a carbon source, and we put these two compounds in the hydrothermal autoclave and heated it at 180 degrees centigrade, I think, for 10 hours. So after cooling, we took out the content and we dialyze through the dialysis membrane, so that any kind of impurities or bigger size of carbon quantum dot can be filtered out. Okay, then be prepared MnO2 nanowires using I think potassium permanganate. Uh, my student can tell better how did she prepare, but I think she is prepared through the hydrothermal route. Okay, so we prepared MnO2 nanowire. Then when MnO2 nanowire is added with carbon quantum dot, the fluorescence of carbon quantum dot is decreases. It means fluorescence quenching happens. Okay, then in the presence of MnO2, the fluorescence of carbon quantum dot is quenched. Using this quenched carbon quantum dot, we added acetylcholine esterase enzyme. Okay, then acetylcholine esterase enzyme and thiocholine. Yeah, I just forget. We added what? Acetylcholine esterase enzyme and acetyl thiocholine. The reactivity of acetylcholine esterase with thiocholine gives acetyl thiocholine gives thiocholine. So thiocholine is sulfur containing compound. Okay, so what this sulfur containing compound will do? This sulfur containing compound will actually reduce the MnO2 to form Mn2 plus ion. And at the same time, this thiol containing compound will be dimerized. Okay, so there will be a sulfur dibond, दो एक bond, ठीक है? This species, then sulfur, then another single bond, then sulfur, then this species. So this molecule will dimerize. Means what? This will be oxidized and MnO2 will be reduced. And as MnO2 will reduce into Mn2 plus, then what will happen? The fluorescence recovery of carbon quantum dot will happen. This is one scheme, and through this scheme, yes, then we added organophosphorus pesticides. The remaining story, you know, I told you in previous experiments. Okay, so the activity of enzyme will inhibited. Then this sulfur containing group will not generate. Then fluorescence quenching of carbon quantum dot will take place. Okay, in another route, what we did, we use this quenched carbon quantum dot, which is quenched through the MnO2. We added glutathione. So what will happen? Glutathione will reduce MnO2 again, and it will form Mn2 plus ion, and this will dimerize. This glutathione will dimerize. Then fluorescence intensity of carbon quantum dot will again recover. In another route 3. Okay, so what we did actually, we use same quantum dot, carbon quantum dot MnO2 to determine the glutathione, the activity of acetylcholine esterase, and pesticides. Now cholesterol. So how cholesterol we determine? Okay, see, so carbon quantum dot plus MnO2. In this system, we added cholesterol oxidase an enzyme. तो कोलेस्ट्रॉल ऑक्सीडेज एंजाइम क्या करता है? कोलेस्ट्रॉल ऑक्सीडेज एंजाइम के प्रेजेंस में we added cholesterol. So what will happen actually in the system? This cholesterol will convert into cholestanone and hydrogen peroxide will generate. And this generated hydrogen peroxide will once again reduce MnO2 into Mn2 once again recover. So utilizing these hypotheses, we designed a carbon quantum dot or MnO2 freight pair for the detection of cholesterol, glutathione, acetylcholine esterase, and chlorpyrifos, which is organophosphorus pesticides. So this is the story. Okay. So how did we perform all the experiments? See. Yes. How did we decide that carbon quantum dot and MnO2 nanowire pair will be a very good freight pair? See, the green line you can see, top left figure. Okay, if you can see, this green line shows the absorption spectra of MnO2 nanowire, and this pinkish line, this figures, this graph shows the emission spectra of carbon quantum dot. So you can see this is the complete space which is being overlapped between the absorption spectra of MnO2 and emission fluorescence spectra of carbon quantum dot. Therefore, we enlarge the size, the size of this figure. You can see the rods very clearly. Yes, we characterize carbon quantum dot through UV visible spectra. See, this is a solder in UV visible spectra of carbon quantum dot, which shows the pi to pi antibonding transition. Okay, see, this is the fluorescence spectra of carbon quantum dot at different excitation wavelength. You can see by changing the wavelength of excitation, the fluorescence spectra shows rate shifted. So this is because of the presence of different kind of groups in the surface of carbon quantum dot. It could be pyrrolic nature of nitrogen, it could be pyridinic, it could be pyridine oxide, or it could be graphitic nature of nitrogen. So I will discuss this later. I have one very good XPS spectra of our recently prepared carbon quantum dot. I will discuss all this. Here you can see the TEM image of carbon quantum dot. The size is around, the size is 4 nanometer. From fringes of this carbon dot, you can see the spacing between two layers is 0.34 nanometer. So here you can see. So what is actually carbon quantum dot? So carbon quantum dots you can consider is a sheet of 3-4 layers of carbon, hexagonal carbon you can consider. ठीक है, तो जैसे हमको पता है कि जो ग्रेफाइट होता है ना, उसमें जो ग्रेफाइट में जो ग्रेफिन के जो लेयर्स होते हैं, ठीक है, तो द डिफरेंस बिटवीन टू लेयर्स आर exactly 0.33 nanometer. So you can see here, जो अभी हम देख रहे थे ना, तो this is what 0.34 nanometer. So using this spacing, we can characterize also the carbon quantum dots also. And from here, IR spectra, you can see we can characterize the different functional group present in the carbon quantum dot. It could be amine group, it could be amide, it could be alcoholic. There should be some acidic group also. Oh yes, so this is again UV visible spectra of MnO2 nanowire. This is IR spectra of MnO2 nanowire. This is what actually, this is for the characterization of MnO2 nanowire, if it is prepared or not. So you know this. This is EDX spectra. This is XRD, and through all these using these data, we characterize the MnO2 nanovirus prepared. This is same. This is TEM, and this is once again TEM image of your MnO2 nanowire. And from here you can see the fringes, the difference between two layers, which is 0.69 nanometer, and therefore what we prepared MnO2 nanowire is a pure. And yeah, these all are the same. Okay, so let's see if there is no slide. Okay, let's go. So this I have already discussed. Okay, using this phenomena, we calculated the Fred efficiency C, and yes, this is XPS spectra, and using this XPS spectra, we actually characterize that MnO2 nanowire is actually the carbon quantum dot is actually adhere on the surface of MnO2 nanowire, so that thread process can happen. Say from this linear regression curve, we calculated the limit of detection of hydrogen peroxide, cholesterol, glutathione, acetylcholine esterase, etc. And using these, we calculated the LOD of chlorpyrifos. Oh, see, this is different information regarding the fluorescence lifetime of the bare carbon quantum dot, and in the presence of MnO2 nanowires. Yes. Recently, we synthesize different, I think three different carbon quantum dot. One was nitrogen doped carbon quantum dot. Another quantum dot we prepared was nitrogen doped and silver co-doped carbon quantum dot. And third one we prepared is nitrogen doped and co-doped with cerium. So what we did, we synthesized carbon quantum dot, which is doped with heteroatom nitrogen and doped with the metal ion like silver and cerium. And after synthesizing that quantum dot, we characterize with a different spectroscopic technique through IR, through UV visible spectra, through fluorescence measurement, through your TEM images, etc. And then we study the XPS spectra of nitrogen dot carbon quantum dot, so it gives a very good amount of information. You see the figure number 1A. So this is what the peaks in XPS. This peak is for carbon 1s, and this middle is for nitrogen 1s, and this is for oxygen 1s. So you all people knows the XPS, X-ray photoelectron spectroscopy. There are two kinds of photoelectron spectroscopy technique: UV photoelectron spectroscopy and X-ray photoelectron spectroscopy. So UV photoelectron spectroscopy is used for studying the functional group of the molecule. Yeah, sorry. Yes, how to say? You understand my point, what I am saying. And the X-ray photoelectron spectroscopic technique is used to study the binding energy of core electrons. Okay, so this XPS is what actually? This XPS are for the binding energy of core electrons of carbon, nitrogen, and oxygen present in the carbon quantum dot, because nitrogen doped carbon quantum dot is comprises of nitrogen, carbon, oxygen, and hydrogen. But hydrogen cannot be treated with XPS. So there is no spectra of hydrogen. Then what we did, we chosen the different peaks of carbon, nitrogen, and oxygen and deconvoluted it. Deconvoluted means expanded it. Then when we expanded, then what we find that among this peak, there are many peaks. 1, 2, 3. Okay. And with this peak, the binding energy are here. And on the basis of this binding energy, we characterize that which kind of carbon are present in carbon quantum dot. So this is CC, C double bond C, CN, COC, and COH. It means at the surface of carbon quantum dot, there could be OH group, there could be CNH2 group or something else. Okay, there could be sp2 hybridized carbon C 6. मतलब एक सर्कल ये बना ना, ये see this I'm saying, if you can see this will be catalyzed through this binding energy. Or there could be carbon single bond. It means if any carbon is at the edge of carbon quantum dot, okay, and there is C double bond OH acid group. So through this binding energy, we characterize this CCC. Very interesting thing happened with nitrogen. You see, nitrogen can be doped in carbon quantum dot seed in different form. See, in the form of pyridinic, in the form of pyrrolic, or it could be graphitic, or it could be in the form of amidic, it could be quaternized nitrogen. So this XPS spectra actually tell us that how different kind of doping of nitrogen is present in carbon quantum dot. And if you remember, I shown you. Let I go to back slide. सी यहाँ आपको दिख रहा है आप लोगों को?
Yes, sir.
हेलो, कोई सुन रहा है?
Yes, sir. दिख रहा है सर.
यस सी. तो ये एक कार्बन क्वांटम डॉट है, ये सी, और इसमें नाइट्रोजन का डोपिंग है. तो सी, if there is only graphitic core of carbon quantum dot, then there will be pi antibonding transition. So pi is what? Homo, and pi antibonding is LUMO. Okay, in between, if nitrogen is doped in graphitic form, मतलब one carbon is replaced by one nitrogen, then it will be graphitic. ठीक है? So there will be another energy state. And other than this, if there is pyridinic, amine like nitrogen, then there will be different energy states in the same carbon quantum dot. So now think, if we excite this carbon quantum dot with the UV light, the electron will go to the LUMO. When it will come back to the ground state, it can directly come back to HOMO, giving fluorescence, but it can, before coming to ground state, can go through different energy states, like a graphitic, pyridinic, amidic, like this. Then what will happen? The fluorescence will shift towards higher wavelength, because the energy gap between this pyridinic and this LUMO is decreasing. So on the basis of these kind of doping of nitrogens, we can actually interpret the different type of fluorescence emission of carbon quantum dots. See, yes. See, this is graphitic sheet, graphene sheet. All the carbons are sp2 hybridized, single sheet, है ना? So what is graphene actually? So graphene is a single sheet of graphite. This is graphene oxide. See, तो अगर इस ग्राफीन शीट में कार्बोक्सिलिक ग्रुप आ जाए, कुछ एल्कोहलिक ग्रुप आ जाए, है ना, और यहाँ पे कुछ ऑक्साइड बन जाए, ठीक है ना, इस लाइक दिस, तो दिस इज कॉल्ड व्हाट? नाउ द ग्राफीन शीट इज ऑक्सीडाइज्ड, okay na, because of the presence of oxygen containing groups. This is called graphene oxide because of oxide sheet of graphene. And this is actually carbon quantum dot. See, this is what? This is 1 2 3 4 5. This is pyrrolic nature of nitrogen. This is pyridinic nitrogen, nature of nitrogen. So through here we can see how the different nitrogens are actually incorporated in the carbon quantum dot sheets. अच्छा, आप लोग सुन रहे हैं मेरी बातें?
Yes, sir. Yes, sir.
Yunus, are you?
Yes, sir. I am here.
Okay, so I have so many things to say. Okay, and अगर आपके पास टाइम लिमिट होगा तो मुझे बता देना, ठीक है? I will stop at the same time. ठीक है?
Okay, sir.
हाँ, मुझे बताना, ठीक है? चलिए, ओके. सो आपने सुना है कि कोई ग्राफीन या ग्राफीन ऑक्साइड जैसा मॉलिक्यूल है, एंड दैट मॉलिक्यूल कुड बी पैरामैग्नेटिक इन नेचर. वंदना,
Yes, sir.
क्या लगता है आपको?
Actually, I couldn't listen to your question due to some network issues. आपकी आवाज से बीच में कट के आ रही है, तो can you repeat it for me?
हाँ, मैं पूछ रहा हूँ कि क्या आप सोचते हैं कि कोई ग्राफीन जैसा मॉलिक्यूल, ग्राफीन ऑक्साइड जैसा मॉलिक्यूल हो, वो पैरामैग्नेटिक नेचर का हो? Is it possible?
Sir, if it will be having any free electrons like graphite has, it can be, I think.
Yes, okay, I am telling you. Yes, possibilities are there. Although all the electrons in graphene sheet or graphene oxide sheet or any organic molecule, all the electrons are paired. Am I right?
Yes, sir.
So if there is pairing of electron, then there could never be paramagnetism. There could only be dimagnetism.
Yes.
Okay, but recently it has been reported with in different journals like MUKMI, International Edition, Nature Communication, that graphene or graphene oxide could be of paramagnetic nature. How? ओके, तो मेरे पिक्चर को जरा देखोगे, जितने लोग देख रहे हैं ध्यान से देखो, ठीक है? सी, मैं जहाँ पे कर्सर रखा हूँ आप देख रहे हैं क्या? सी, ये दिख रहा है? ग्रेफीन ऑक्साइड आपको दिख रहा है जहाँ पे ग्रेफीन ऑक्साइड है?
Yes, sir.
ओके, सो ग्रेफीन, ये जो मैंने जो ग्रेफीन ऑक्साइड दिखाया हुआ है इसको ध्यान से देखिए, और इसमें जो मैंने कार्बोक्सिलिक एसिड ग्रुप या जो लगाया हुआ है, यू फॉरगेट दिस फंक्शनल ग्रुप and you see the picture from here, and I'm moving my cursor, if you can see like this. See, ये मैंने मूव किया अपने कर्सर को, आपने देखा? तो ये जो सीट है ये बहुत बड़े ग्राफीन सीट को काटा गया है, समझ लीजिए, ठीक है? दिस इज वन वे टू कट द बिगेस्ट ग्राफीन सीट इनटू स्मॉल ग्राफीन ऑक्साइड, स्मॉल सीट. दिस इज वन वे. एंड सी फिगर फ्रॉम टॉप, सी मैं दिखा रहा हूं, देखिए ये दिस इज कार्बोक्सिलिक ग्रुप, और यहाँ पे देखिए वन टॉप डाउन टॉप डाउन टॉप डाउन टॉप डाउन. यू सी?
Yes.
सोच के देखिए, when this seat will terminate from here, and what will happen when this seat will terminate from here? लेफ्ट हैंड साइड से टर्मिनेट होगा और ये टॉप साइड से टर्मिनेट होगा. देन जब ये इस तरह से टर्मिनेट होगा तो इसको बोलते हैं जिगजैग एज. सी, जिगजैग दिख रहा है, जिगजैग एज. एंड ये लेफ्ट हैंड साइड से जो दिख रहा है, दिस इज कॉल्ड आर्म चेयर एज, आर्म चेयर. Okay, so if any graphene seed is terminated through the zigzag edge, see, so this carbon, ये जो कार्बन है, ये वाला कार्बन, ये there is one bond with another carbon, this another bond with carbon, but now there are two remaining bond which is not present. ठीक है? तो this is actually what this will function as a what? Carbene. Okay, so this will be what? Like carbene, and if it is carbene, then the triplet state of carbene is most stable as compared to singlet state carbene. Am I right, Vandana?
Yes, sir. Yes, sir.
Okay, very good. तो the triplet state में जो carbene है, that is most stable. तो अगर ऐसा situation आ जाए कि triplet state में ये जो carbon है, that contains single electron, then what will happen? Whole system will become paramagnetic.
पैरामैग्नेटिक.
यस, ओके. जो ये जो आर्म चेयर वाला जो आपको मैंने दिखाया, ये इस तरह का जो टर्मिनेशन है, इसमें ये दिस दो कार्बन के बीच में जो बॉन्ड है, इट बिहेव्स लाइक अ कार्बाइन, ठीक है, नॉट कार्बीन. और ग्राउंड स्टेट इज सिंगलेट. इसका जो ग्राउंड स्टेट होता है वो सिंगलेट होता है. तो जब सिंगलेट होगा तो देयर विल बी पेयरिंग ऑफ इलेक्ट्रॉन, देयर विल बी नो पैरामैग्नेटिज्म. सो दिस इज एक्चुअली रिसेंटली रिपोर्टेड in different journals. So it is amazing to know that any carbonaceous material can have paramagnetic properties. Okay, so I go further. Yes, so I will give you 15 minutes more. Okay, it is okay?
Yes, sir.
Yes, sir. Okay, so okay, what we are recently doing, ठीक है? ये जो अभी आपके पास एक फिगर दिख रहा है, ये सी, ठीक है, ये अच्छा, ये आप जानते हैं कि हाउ गोल्ड नैनो पार्टिकल गिव्स सरफेस प्लाज्मो रेजोनेंस स्पेक्ट्रा, है ना? तो दैट स्पेक्ट्रा इज बिकॉज ऑफ व्हाट? व्हेन गोल्ड नैनो पार्टिकल कम्स इन कांटेक्ट विद रेडिएशन, ठीक है, द इलेक्ट्रॉन क्लाउड ऑफ गोल्ड नैनो पार्टिकल इज पोलराइज्ड. ओके, तो एक तरफ नेगेटिव चार्ज हो गया, दूसरी तरफ पॉजिटिव चार्ज हो गया. जो नेगेटिव चार्ज वाला जो क्लाउड है गोल्ड नैनो पार्टिकल का, देन द ऑसिलेशन ऑफ दैट इलेक्ट्रॉन, सरफेस इलेक्ट्रॉन, interact with the electromagnetic radiation and gives absorption, and it gives absorption at 520 nanometer. ओके, तो एक राउंडेड गोल्ड नैनो पार्टिकल है. ये मैं डायग्राम है क्या मेरे पास में? नो, इट्स नॉट हियर. ओके, नो प्रॉब्लम, ठीक है. तो उसका ऑसिलेशन से क्या मिलता है हमको? एक सरफेस प्लाज्मो रेजोनेंस बैंड मिलता है. अब सी there is nanorod. This is gold nanorod. It looks nanorod ना, rod इससे दिख रहा है, ठीक है? तो ये जो गोल्ड नैनोरॉड है, ये जब इलेक्ट्रोमैग्नेटिक रेडिएशन के इंटरेक्शन में आएगा, तो इसका जो इलेक्ट्रॉन क्लाउड है, इसमें दो तरह का पोलराइजेशन हो सकता है। सी कैसे? व्हेन ये वाला जो एज दिख रहा है, टॉप वाला एज, ठीक है ना, इस दिस विड्थ में जहां पे माइनस चार्ज आ जाए, इधर पॉजिटिव चार्ज आ जाए, एक कंडीशन ये हो सकता है। दूसरा क्या हो सकता है कि दिस एंड विल बी पॉजिटिवली चार्ज, दिस विल बी नेगेटिवली चार्ज, ठीक है? तो इन द कंडीशन व्हेन दिस विड्थ में पोलराइजेशन आ जाएगा, तो इसके साथ इलेक्ट्रोमैग्नेटिक रेडिएशन के इंटरेक्शन से वी विल गेट अ प्लाज्मोनिक बैंड व्हिच इज कॉल्ड ट्रांसवर्स प्लाज्मोन बैंड, ठीक है? और जब इस तरह का पोलराइजेशन होगा, एंड टू एंड पोलराइजेशन होगा, देन इसके साथ इलेक्ट्रोमैग्नेटिक रेडिएशन का जो इंटरेक्शन होगा, देन वी विल गेट longitudinal plasmonic band. It means what? Means if we take the UV visible spectra of gold nanorod, it gives two bands, one at 520 nanometer like a gold nanoparticle, and another it gives at around more than 650 nanometer, and that is because of what? This length of nanorod. Okay, so ये हमको पता था, दिस we prepared gold nanorod, और हमने ये इसका UV visual spectra लिया, we understood that yes there will be two kind of the bands what we hypothesized. अच्छा, okay, see, yes, अगर इस गोल्ड नैनोरॉड में अगर ईचिंग कराया जाए, ठीक है, तो कैसा हो सकता है इसका ईचिंग? अगर इसका ईचिंग कराया जाए तो उसको इसका जो विड्थ है वो कम होता जाए। इसी फिगर 1A, सॉरी फिगर A, so width is decreasing. So when width will decrease, the absorption at 520 nanometer will decrease. And if the etching is happening as such that the length of gold nanoparticle is decreased, see here, red color. So the longitudinal band will decrease. The absorption of this band, longitudinal band, will decrease. ठीक है? और अगर मान लो इसमें पूरी तरह से ईचिंग हो जाए इसमें, तो ये दिस विल बिकम स्फेरिकल लाइक गोल्ड नैनोपार्टिकल, देन व्हाट विल हैपन? दीस लॉन्गिट्यूडनल बैंड विल कंप्लीटली डिसअपीयर एंड देयर विल बी ओनली व्हाट? absorption at 520 nanometer. That is only for what? Gold nanoparticle. So utilizing this phenomena, this, okay, we designed one thread based process. What we design? We prepare carbon quantum dot, 4 carbon quantum dots: blue emissive, green emissive, orange emissive, and red emissive. Okay, and we try to see that if carbon quantum dot is blue emissive, then there could be a little bit overlap with the absorption spectra of gold nanorod at 520 nanometer. And this is remain. I skip this. Okay, you consider only this figure. Okay, then green. See, the green carbon quantum dot emit at 520 nanometer. So this fluorescence spectra of carbon quantum dot is exactly overlapping 100%, close to 100%, overlapping with the first absorption band of gold nanorod. Then orange. तो orange का जो कार्बन क्वांटम हमने बनाया, that gives emission in which it is partially overlapped with the 520 nanometer band and partially overlapped with the 650 around band of gold nanorod. And see the red one. So red emissive carbon quantum dot, the fluorescence of red emissive carbon quantum dot is not overlapping anymore with the 520 nanometer band of gold nanorod, but it is somehow some amount of overlapping is there between fluorescence emission of carbon quantum dot and gold nanorod. So on the basis of this, we developed a sensor for determination of glucose and cholesterol. So the work is actually going on. We have not till reached to the conclusion soon we will have more amount of data, and definitely we will have a good paper. And this is the process lifetime measurement of carbon quantum dot. All the carbon quantum dot, blue, green, orange, and red in the presence of gold nanorods. So from these all these data, we can conclude that the process lifetime of all the carbon quantum dots are decreasing in the presence of gold nanorods. That means the freight process between carbon quantum dot and gold nanoparticle is happening, but what amount of freight process is happening, that is really depends upon the overlap integral between carbon quantum dot and the absorption band of gold nanorod. So soon we will have good paper. I believe one of my student, she is a PhD Inspire Fellow. She is actually a gold medalist. She is working on this field, and hopefully she will do good. With this, I think it's a very long lecture. 1.5 घंटे कुछ हो गया, तो मुझे लगता है कि शायद यहाँ पे कंक्लूड करना चाहिए. यूनुस.
Sure, sir. It was a wonderful lecture.
Okay. So let I thank first. Okay, so thank you very much for your patience listening and giving your time to listen my lecture. And I was very happy, even happy to interact with you people, as I told you earlier. And whenever an opportunity is given to me to interact with you in a physical mode, I will be very happy. With this, thank you very much.
So actually, we also were looking forward to, attending this session or sessions of this kind in physical mode. And I must say, I am not, I am unaware of the vast field that nanochemistry is. And for a student like me who is unaware of even the basics, you have started with very basics of the techniques and what nanoparticle, quantum dot particle, etc. they are. And then you gradually, step to the advancement of your work. And it was a very knowledgeable, yet simple and effective session. And now I told you, I announced that the session is open for discussion. You can ask any queries if you have to sir. And
So may I? May I say?
Yes, please.
Good afternoon, sir. So it was a very nice presentation. Actually, it was relating to my topic, so I felt very interesting, and the concept you took was so nice. So may I ask a question on this acetylcholine? This is the neurotransmitter. This causes the nerve synapses.
Yes.
But
yes.
in human body, we have the acetylcholine. We don't have the acetylcholine. So what is the purpose of you taking acetylcholine and not acetylcholine?
Actually, acetylcholine is a molecule which doesn't contain thiol. Okay, so our work is actually to design a mechanism. Okay, so using acetylcholine, we cannot do this because it doesn't contain thiol. So thiol is actually, how to say, thiolcholine. What we can say. I'm forgetting the word. Very good.
We have the sulfur group attached in place of oxygen. We have the sulfur group attached in the acetylcholine molecule. Yes.
Yes.
But then our body cannot recognize, because our body can recognize only the acetylcholine, not the thiolcholine. So will it be possible to detect the organophosphates then?
See. Our objective was to detect the pesticide. Okay.
Yes, sir.
And for the detection of pesticide, we designed the sensor. And we use the acetylcholine esterase enzyme. Okay. So that we can monitor the activity of acetylcholine esterase also. Okay. So what was the purpose? To detect the pesticides, to study the activity of enzyme. और आपको पता होगा एसिटिलकोलाइन एस्टेरेस एंजाइम की एक्टिविटी को एनालिसिस करने के लिए आई थिंक पैरानाइट्रोफिनॉल इज यूज्ड element reagent, I think I forget. Oh, forget. Okay. So this was
Yes,
our
shown on
purpose.
slide.
So okay. So हम using our nanomaterial, we can check the activity of acetyl esterase enzyme. We can detect the pesticide.
Okay.
Instead of using acetylcholine, we used a simulant, the similar like molecule, acetylthiol.
Fine. Okay. It was a nice concept, sir. I have more questions, but I shall be talking to you, sir, somewhere in the next time, sir. Thank you
Sure.
so much. Thanks for
Please.
a nice
Thank you.
presentation, sir.
Please. Thank you.
If any other one wants to ask anything, you can still ask, sir.
Better you people. I will give you my email ID. I think you have my email ID, Vandana.
Yes, sir. I am having your email ID. I'll share it in the group. If you wanna, personally, if you wanna ask questions and know about the field, you can contact sir on his email ID.
And we
Yes,
can have
sure.
collaborative work.
Thank you.
Thank you. So may I leave now, Vandana?
And sir, let me thank you. So, on the behalf of our organizing team, I would like to extend my sincere gratitude towards you, sir, that you gave us your precious time and a wonderful chance to interact with you and understand the work, the very good work you are doing in your field. And I definitely, you know, I always want to learn, and it was always my, you know. Wish that I can do that kind of the research work which you are doing with you, and maybe in future I get a chance, and I'm looking forward to it. And I express my heartfelt gratitude towards all the participants who attended this session for their valuable time and contribution. And concluding the session, I would like to briefly tell you about tomorrow's session. Tomorrow, too, we will be having a great personality. His name is Dr. Chitranjan Das. He is Chief Technical Officer, Entrepreneur, Solar Cell Persosol Startup Germany. And I invite in advance. I invite you all to tomorrow's session. And at last, I again thank Dr. Manmohan Lal Satnani sir for being with us today and giving his valuable time. Thank you so much. You all have a great day.
Thank you. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you. Thank you. Thank you.